That means that you have more cosmic rays as you move into the spiral arms.
If we look at the Milky Way from the top, what we'll see are 4 spiral arms, and that's because the Milky Way is a spiral arm galaxy. So we have 4 spiral arms. We are located here on some small armlet. We are rotating around the sun once every year, but the whole solar system rotates around the Milky Way once every about 250 million years. That's one galactic year. What this means is that every 150 million years, when we pass through a spiral arm of the galaxy, it's colder by something of order 5 degrees or 10 degrees. When we're outside of the spiral arm, it's hot. Now we're on this small spur, so we're witnessing cold weather. When we enter a spiral arm of the galaxy, we are going to witness more cosmic rays reaching the Earth, more atmospheric ionization, more cloud condensation nuclei, and therefore more low-altitude clouds, or to be more precise, whiter low-altitude clouds which better reflect the sunlight and cool the Earth. So the bottom line is that when we enter a spiral arm of the galaxy, we should expect lower temperatures. 100 million years ago, these cliffs were part of the floor of a warm ocean. Earth back then was between spiral arms of the galaxy. All over the Earth, it was much warmer. We had dinosaurs sunbathing in Alaska or in Antarctica. About 70 million years ago, we started approaching and entering the Sagittarius spiral arm, and Earth became exposed to a higher flux of cosmic rays because of all the stars around us. This larger flux of cosmic rays was responsible for the formation of more clouds and colder conditions here on Earth. The ice sheets that later formed, they actually pushed all those cliffs out of the water like bulldozers, and they rippled the landscape. So what we see here in these cliffs is a good example for hot conditions on one hand when those cliffs were formed, and cold icehouse conditions which we have today, which are responsible for the uplifting and current conditions of these cliffs. It may sound strange to most people that we're talking about icehouse conditions today, but if you look on the long time scale, you find that during most of Earth's history, we didn't have any ice caps whatsoever. Today we have. 450 million years ago, we had very cold conditions here on Earth. However, we had more than 10 times as much CO2 in the atmosphere. So clearly CO2 is not a major climate driver, at least it wasn't a major climate driver then.
When we talk about climate changes on these timescales, it is a kind of climate change that is much, much more dramatic than anything we have seen in our history. When we are in between spiral arms, it looks as if we are in a warm period called a hothouse, and most of the ice is simply melted. There's no ice at all. When we are in the spiral arms, half the area of the Earth is simply covered with ice. And the changes in climate, are much, much more dramatic than anything we have seen recently.
Over the past billion years, Earth has passed through periods when it was cold and periods during which it was hot. And lo and behold, the periods during which it was cold synchronize with the astronomical data, which tells us when we should have passed through spiral arms of the galaxy. At some point, I realized that you can actually reconstruct the cosmic ray flux, and you can do it with these things, with the iron meteorites, because iron meteorites, after they break off their asteroids, they're exposed to cosmic rays, and they record the cosmic rays in the solar system over hundreds of millions of years. And what you find is that this cosmic ray flux changes exactly as you would expect from the astronomical data on one hand, and it also changes exactly in sync with the climate variations that you can reconstruct using geological record.
I've been working almost all my life on issues related to environment. And of course, one of the biggest problems and issues was what was the climate and how the temperature of the seawater changed. And we worked on the fossils like this, called brachiopods. These shells record the temperature of the past oceans. When they form, they reflect the temperature of the ocean water because they build in the atom of oxygen. Then you could measure this proportion of oxygen, and you could get a measure of the temperature of the past oceans, and that means of the temperature of the Earth and climate. So when we can measure this, we would get a record of ocean temperature for 500 million years. When I look at the data, I realized that actually there were some oscillations in the general trend of temperature, and that those oscillations fitted quite well with what we knew from geology, what kind of a climate was at that time. Working with the colleagues, we did an evaluation and statistical study of that, and we saw that there was some kind of a periodicity, roughly, of about 140 million years, switching back and forth between hothouse and icehouse. I suspected that the reason for this rough periodicity was something to do with the sky. But I was searching for it and couldn't find anything. So essentially I gave up. I didn't have an explanation.
Jan Weiser, he reconstructed the temperature using geochemical records. And the difference between that reconstruction and what I was using is that Jan Weiser actually reconstructed the actual temperature. So he knew exactly how warm it was and how cold it was. So I emailed him.
One evening, I was sitting in my office working. Suddenly, an email popped up, and this was near Sharil. And he says, well, I may have an explanation for you. He was telling me that he was working on cosmic rays variability over the more or less the same time intervals, and that the variability in the amount of cosmic rays hitting the Earth over this time interval was more or less similar to the variation in those oxygen atoms or in the climate which we observed.
After I teamed up with Jan Weiser, we had an actual temperature reconstruction. And what we could learn was that it was colder here on Earth by something like 5 to 10 degrees when we were inside spiral arms of the galaxy. Nobody found anything like that before, and we were simply amazed from it. But more interestingly, what it means is that cosmic rays are the main climate driver on Earth, at least on geological timescales. And the only explanation you have for it is the Sevensmark theory about the cloud cover. When you compare the geological record to the astronomical record, that's what you get. You see that the two barcodes give you the same product. The black line is the geological reconstruction of the temperature on Earth using the geochemical records of Jan Weiser. And what you see in the red is the cosmic ray flux variations. When both things are added together, they correlate very well. Statistically, it's very significant, but you don't have to believe the statistics. You can just look at it and realize that it's very meaningful.
It's been said so many times that the sun has not been responsible for the heating we have seen the last maybe 20, 40 years. However, if you look at the data, for instance, the ocean data, you will actually see that there's a very good agreement between temperatures and solar activity. And what you see is the temperature of the ocean down to about 50 meters. But if you compare the overall agreement with how the red curve is varying, it's very good. And the red curve, that is the cosmic rays. That is how the cosmic rays have been varying over this period. So we actually see, even today, that the sun is dominating the temperatures or how temperatures evolve. It has done so in the past, it's doing this now, and will also do it in the future.
An experiment like the one taking place here in Copenhagen is crucial because if successful, it will shed a lot of light on the physical origin of the link between cosmic rays and climate. And this will be the last piece in the puzzle which would make the picture complete.
So the effective aerosol background corresponds more or less precisely to what you have over the ocean. The experiment is not just something that you turn on and then you get the result. You get many, many results, and you do a lot of experiments, and you try to see if everything is consistent with that interpretation that you are giving.
The results of this experiment, hopefully we will know exactly how the sun affects climate, how it modulates the cosmic rays reaching the Earth, how cosmic rays control the amount of ionization, and how ionization controls climate, and through most probably formation of cloud cover.
It's very interesting after nearly 8 years of work that we finally got to this phase of trying to understand these experiments. All the bits and pieces was done over nearly a year. So it's not like from one day to another you sort of a sudden jumps up and says, fantastic, we got the result. It's not like that. It's actually hard work. Don't you think? I mean, there's always a degree of uncertainty when you do experiments because you are constantly questioning everything you're doing, whether it's right and wrong. But we have been very, very careful, and we have done many, many tests on these ideas. So I think, I truly think that we have found a very, very important mechanism. And the mechanism was a big surprise how it actually worked. It's far back. I mean, this is 0.34 ppb. Wow. So it's very, very low. What we find when we mimic a higher flux of cosmic rays is that we actually produce more aerosols in the chamber. This actually means that cosmic rays are producing aerosols, and these are the aerosols which are responsible for forming clouds in the real atmosphere. Through our experiments, we have found a new form for atmospheric chemistry, which we think is responsible for the formation of new aerosols and therefore also for clouds in the Earth's atmosphere. And it shows that events in the universe are driving climate here on Earth to an extent that has never been understood before. A large part of the clouds that we see in the sky is really a result of this process that we have investigated experimentally. But of course, now we have to see how other colleagues react to our findings, and that will be very interesting to see how this work will be received But I think we have done a very good work, and I'm very pleased that, how